I'm Pat Dugas. This screencast is about using exponential and logarithmic functions to model exponential growth and decay. Exponential growth can be modeled with the formula f of x equals a times e to the kt. And a is your starting value. K is going to wind up being the rate of growth, and t is the amount of time that is taken place. Exponential decay can be modeled with a similar function, ae to the minus kt, where minus k is the rate of decay. To be able to figure those equations out, we need to find out the rate of growth or decay in the situation. Let's look at a continuous growth situation in the population of China. In 2007, the population of China was estimated to be 1.32 billion. However, in 2000, it was 1.26 billion. So we needed to determine the value of k, which is China's relative rate of growth, assuming that that growth is exponential. So we're going to use that formula for continuous exponential growth, ae to the kt. And since we know that in 2007, the population was 1.32 billion, its initial population in 2000 was 1.26. That's the a value, the starting value. And 7 years have taken place between 2000 and 2007. The unknown part is this k, which is going to be the rate of growth. The first thing we're going to have to do is isolate the e by dividing both sides by 1.26. When we do that, we get 1.32 over 1.26 equals e to the 7k. So we take the natural log of both sides. The natural log of 1.32 over 1.26 equals the natural log of e to the 7k. And because the natural log and the e are inverses of each other, this means the natural log of 1.32 over 1.26 equals 7k, because the natural log of e to the x is equal to x. So k is going to be equal to the natural log of 1.32 divided by 1.26 divided by 7. And once you do that carefully in your calculator, you're going to get that k value, the rate of continuous growth, is 0.0066, which, multiplying it by 100% to get a percent, means China between 2000 and 2007 grew at an annual rate of 0.66%. So a question occurs, when will China's population reach 1.5 billion? So now that we know the rate of growth, if we assume that that rate of growth continues, k is now 0.0066. It's a big assumption to assume that it's going to continue at that rate, but we go 1.5 equals 1.26, the 2000 population, a, times e to the 0.0066t. Again, we're going to divide both sides by 1.26. And that gives us approximately 1.1905 is approximately equal to e to the 0.0066t. Take the natural log of both sides, and you get the natural log of 1.1905 is approximately equal to the natural log of e to the 0.0066t. Since the natural log and e cancel each other out, we wind up with the natural log of 1.1905 is approximately equal to 0.0066t. All we have to do is divide both sides by that coefficient in front of the t, and we get that t is approximately equal to natural log of 1.1905 over 0.0066, which means 26.42 years. Now, if we add that to 2000, that means in approximately 2026, China's population will reach that 1.5 billion mark. Let's look at an example of dating things through the concept of half-life. A half-life of an isotope is the amount of time it takes for that quantity to decay to a value of 1/2. In other words, if I had 100 grams of sodium-22, since sodium-22's half-life is 2.6 years, after 2.6 years, I would only have half of the 100 grams or 50 grams left because the rest will have decayed. So to determine the decay equation, we have to determine the value of k in the formula y equals ae to the minus kt. Negative sign there is because it's a decay. So after that 2.6 years, t is 2.6, that y value has decayed to amount half of its original value, 0.5 times that original value, or a. And we can divide both sides by a, and the a's cancel out. And so what we're left with is 0.5 equals e to the minus 26 times k. Next thing we're going to do is take the natural log of both sides using that property of equality. And so we get the natural log of 0.5 equals the natural log of e to the minus 2.6k. Well, the natural log and the e cancel each other out. The natural log of 0.5 equals minus 2.6k. We're going to divide both sides by negative 2.6. And that's going to give us the natural log of 0.5 divided by negative 2.6 equals k. When we calculate that, you're going to get a k value of 0.2666, repeating approximately. So the equation of decay for sodium-22 is y equals a e to the minus 0.2666t, where a is the original amount and t is the time in years. So let's use that. Suppose we were examining a meteorite that fell near the high school, and we estimated that that meteorite contained only 10% as much sodium-22 as it would have contained when it reached the surface of the Earth. So the question becomes, how long ago did the meteorite actually reach the surface of the Earth? We're going to use that formula for decay that we just developed, and we know it's 10% of the original amount. So we're going to replace y with 0.1a because 0.1 is 10%. We're going to divide both sides by a, allowing the a's to cancel out. So 0.1 equals e to the minus 0.2666t. Now we're going to take the natural log of both sides. The natural log of 0.1 equals the natural log of e to the negative 0.2666t. The natural log and the e are inverses of each other and will cancel out because the natural log of e is 1. And we get the natural log of 0.1 equals negative 0.2666t. Now we're going to divide both sides by negative 0.2666. And if we divide both sides by that negative 0.2666, we get 8.64. So approximately 8.64 years ago, that meteor reached the Earth. The last thing we're going to look at is a type of function known as logistic growth. In logistic growth, a population increases exponentially at first, and you can see that exponential increase, but then it begins to level off. So it kind of grows in two phases. It's exponential growth, and then it begins to level off. It's important to note that many populations have a logistic growth model because they grow quickly at first, but then the environment and other constraints limit the growth. And in fact, that very top number is known as its horizontal asymptote. That's its limit. That's the number that's going to be in the numerator of the logistic growth equation. And logistic growth is represented by some constant c, which represents that limit, divided by 1 plus ae to the minus bt. And together, that model is a very powerful and useful one. Let's look at an example. Let's say a city's population in millions is modeled by a logistic growth function, 1.432 over 1 plus 1.05 e to the minus 0.32t. And t is the number of years since 2010. If we were to graph that, we would see that limiting value come into play. And in fact, it's this number right here. 1.432 million is the limit, the horizontal asymptote of the logistic function. So that city's growth, probably due to resource and geographic constraints, is limited to approximately 1.432 million. In this screencast, we've looked at using exponential functions and logarithms in helping us deal with exponential growth and decay situations.